Hey everybody, this is Mr. Ainsworth. We're going to get into a topic dealing with how to find the volume of solids of revolution using what's called the disk method. Okay, so once again, we are about to go into how to find the volume, okay, so volume of what's called a solid of revolution. So we've got to talk about that using a particular method, our first one of three, called the disk method. Later on, we'll talk about the washer method, and then in the second lesson. And in the third lesson, we'll talk about the shell method. But right now, we're going to be focusing on a particular method called the disk method. So what is a solid revolution? What is that? Okay. Well, basically, what we want to do is we want to take a region, okay, a bounded region, given by obviously a set of functions here. So we'll take this bounded region here given by x equals 2 divided by y equals 1 and y equals 4 from 0 to 2. And we want to revolve that around the y-axis here. That's what this arrow is all about here. We want to revolve it around an axis, like the y-axis, to get what's called a volume of solid revolution here. In this case, when you take this blue region here, which is basically congruent or the same as this one over here to the right, and you revolve it around the y-axis in this fashion here, either clockwise or counterclockwise, you get a solid of revolution. And the question is, how do you find the volume of that? Well, what we're going to do is develop a method called the disk method. But first, let's define what a solid revolution is. Basically, what I said is that you take it's a bounded region here. All right, in the xy plane, All right, revolved. Okay, so you take this bounded region in the xy plane and you revolve it around a given line called the axis of revolution. So it is a bounded region in the xy plane, revolved, okay, about a given line, which is called the axis of revolution. Now this axis could be the y-axis or the x-axis or any other horizontal or vertical line. It could be y equals 1, x equals 4, y equals negative 2. It could be anything. But this line that we're going to revolve about is called the axis of revolution. Okay, now where do you see this? Well, in reality, the applications are vast, actually. Okay, so let me just list a few here. Anything that's formed on a lathe, either in the engineering field or in the carpentry field, is a solid revolution. You see that in axles, okay? You see that in funnels, pistons in a machine engine, okay? Pistons, valves, another good example. If you've ever seen a valve in an engine, kind of like this shape right here with a hole through it, though, it is a solid revolution. And basically anything made from a lathe, anything made from a lathe. And if you've never seen a lathe, L-A-T-H-E, then go ahead and Google that, and let's highlight that word. Google that and take a look at all the different things you can make on it. Like usually if you see the curved legs of a table that are all nice curved shape, or the legs of a chair, or many pieces of furniture that are made out of wood, they're made on a lathe, and those are what are called solids of revolution. Like I said, just Google lathe and take a look at it and you'll see what I'm talking about. The question is, how do you figure out the volume of a solid of revolution using what's called the disk method? So let's take a look at this. It's actually a pretty simple idea. And what we're going to do is we're going to try to figure out a way to calculate the volume of this figure that we have in here. It's basically the same as what we have up here in the beginning, just rotated or revolved around the x-axis as opposed to the y-axis. I found this app on the internet, and what I did is I clipped out a couple sequence of events showing how to basically divide this up into what are called disks to approximate the volume of the solid. So in this first picture here, we've got picture 1, 2, 3, and 4. This picture right here shows how you can slice up a solid into disks. Okay, in this case we have n equals 5 right here. 5 disks, n equals 5. Just write it down there so you can see better. And what we can do is we can figure out the volume of this disk, which is pretty simple. It's basically a cylinder on its side. We use it in the basic geometry formulas from the past. We take the base area, which is a circle, which is pi r squared, and you multiply how thick it is or how high it is. And then what you do is you find the volume of each disk, in which case this has 5. You sum them up and you get the approximate the approximate volume of the solid. But as you can tell, it's a rough approximation because we only divided it up into 5 disks. So how do you improve that? Well, you go from 5 to 10 or from 10 to 50. Again, this is n equals 10. This is 10 disks. This is n equals 50 disks, and this is n equals 100. And when you increase the number of disks, what's happening is that the thickness of the disk decreases, and the error decreases here too in respect to the total volume, and you get closer and closer to the exact volume. And then if you slice it up into 1,000 disks, you'd get even a better approximation. So how do you do this? How do you get the best? How do you get the exact volume? Well, what you want to do is you want to slice it up infinitely thin and do that an infinite number of times and sum up the infinite number of volumes. We could do that through integration. Okay, so what we need to do is review from geometry how you find the volume of a disk, which is actually a cylinder. Okay, and remember that. A disk is a cylinder. Let me write that down. A disk, okay, back in geometry was called a cylinder. It is a cylinder. So what we need to do is recall from geometry how we do that. Well, the way we did that back in geometry is that you take your base area here in yellow, and you've given the radius here. Okay, you take that and you find the base area. And the area of this, the base area, is, since it's a circle, is given by pi r squared, pi times the radius squared. And you multiply it by how thick it is, or how tall it is. You take the base area times how, well, back in geometry you call it height, but we're going to call it thickness here. Okay? This thickness right here, it's actually a difference of 2x values on the, if this is the x-axis right here, all right, is the delta x. And delta x just stands for x2 minus x1. It's a difference of 2x values. And in the integral, it's going to become the dx, okay, which represents your thickness. Thickness of the disk. So to figure out your disk volume, it's pretty simple. We're going to do it the same way we did in geometry. So let's write this out. What's the idea? What's happening here? The disk volume is given by the area of the disk, the base area, which is a circle now. It's pi times radius squared. So it's pi times radius squared times how thick it is, and I call that dx over here. So base area times thickness. Same thing you used back in geometry, but back in geometry you call this distance here the height. Okay, well, in calculus we call that delta x, or dx in the integral. So how do you sum these up? Well, and how do you find the volume of the solid? Okay, let's talk about that. So the volume of the solid can be approximated by summing these volumes of the individual disks up. We do that by the summation. So let's say that we have a sum of the first, let's say n disks. So I goes from 1 to n of the first disk. Okay, and what we want to do is, again, take the base area times how thick it is. So in general, we say that it's pi times the radius now, which is a function of x. So I'm going to write it as r for radius here, r of x. All right, quantity squared times how thick it is, dx. So this right here, the summation sign, remember it's the sum of the first n disks here, where n could be 5, it could be 10 in this case, 50 in this case, 100 in this case. In general, it could be 1,000. You can run up to 1,000,000. You can do whatever you want. All right, but we want to sum them up from I equals 1 to n. So let's put the index here, x sub I, and let I go from 1 to n, where n could be 5, 10, 50, or 100. This will give us the approximate volume. Again, this is only approximate. Let me write that down. It's approximate volume here. But in reality, of course, we want the exact volume. So the question is, how do you do that? Well, you let run to infinity. That's exactly what you do. You let it go infinitely thin on the disk. You divide it up in an infinite number of disks, which makes the thickness shrink to 0. You sum them all up by the integration symbol, and you find the exact volume. So let's write that out. So the exact volume now, the volume exact, or the exact volume, in this case, would be if we took the limit of this as n goes into infinity. So I'm going to take the limit as n goes to infinity, which means that we're going to have an infinite number of disks here, which is going to force the thickness, again this is thickness now, delta x, it's going to force the thickness right here and right here to go to 0. So delta x is going to shrink to 0, or the thickness is going to shrink to 0. And then we're going to take the infinite sum from 1 to n, where n travels to infinity, of all these volumes. And the volume is pi times the radius, which is a function of x, x of I here, squared, okay? Pi times the radius squared. Again, the radius is not a specific value, so don't think it's a real number here. It's actually a function of x. So we got to write it as r of x, not just a specific value, times how thick it is. All right. So remember, this right here is your base area. Okay, this is the area. All right, times thickness. All right, that'll give you volume. The summation sums them up, and this limit will make the thickness go to 0 and increase n to infinity. Well, in reality, that right there is equal to the integral from a to b now, given the bounds. Let's say a here to b here. Whatever the bounds of the situation is. You got to take a look at the situation at hand. So the integral of pi times the radius as a function of x squared, and again the dx in the integral, well, the delta x becomes the dx in the integral. So this represents your thickness. Okay, and this right here is your area of the base area. So you got to understand geometrically what's happening here. Pi r squared gives you the area on the top of the disk times the thickness dx, and the integral sums them up for you. So you remember the integral is actually just an infinite sum. And that, my friends, is the exact volume. Okay? This is exact. Okay, now when you do this, there are two types of situations that arise. So let's hit them both. Depending on the axis of revolution, the disk method goes as follows here. Let's suppose you have a horizontal axis. Okay, so let's draw one here of revolution. And let's say that our function here, let's make it really simple here. Let's call this f of x here. And let's suppose that the bounded region runs from a to b. And they're going to give you the bounds here, guys. You're going to have to graph this bounded region just like you did in previous lessons. And let's say that this region right here is the bounded region, given by the function, given by the x-axis from a to b. And then a to b could be 0 to 4, it could be 2 to 5, it could be -1 to 7. It depends on the problem. You just have to read it and go with the flow. You graph this bounded region, and let's suppose we want to revolve it around this horizontal axis. Okay? It's revolved here. Well, what's going to happen? Well, what's going to happen is this. This point here gets reflected down here. This point gets reflected down here. And your region now is down now below. That's a little bit off, but that's close enough. It's below the axis. And what's going to happen is that you're going to have these disks. I'm going to just draw a couple of them. And just show what the volume of the solid looks like in 3 dimensions. And it's going to be, no, it's not quite a cylinder. It's kind of like the top of a bullet, let's say, with the top portion cut off flat. So it's got two flat surfaces that are circles, top and bottom, one small, one big, and it's curved and it's solid. Okay, what does the disc look like? Well, let me just show a cross section here. Okay, so this right here is one disc. Cross section. And so what we need to do is find the volume of that disk and then sum them up from a to b. And when you do something like this thickness right here is dx. It's a difference in x values. All right, because of that, you're going to have an integral involving functions of x and a dx type integral. So our volume formula for this one is going to be the integral from a to b. Those are the bounds of integration right there. Pi times the radius as a function of x, right here, squared, dx. Again, that's because the disk is vertical and the thickness is the difference of 2x values. This all changes, though, when you have a vertical axis of revolution. Okay, the disks are not vertical, they're horizontal, and that involves a dy integral. So let me take a look at that. So in this case right here, let's suppose you have a vertical axis of revolution. And let's suppose that let's suppose that your function looks like f of x here. And let's say we're bounded from, well, not a, let's use different variables here. Let's say we're bounded from c to d. And we have this bounded region. All right. Well, what's going to happen, or what does it look like when you revolve around the vertical axis here? Well, let's kind of draw that and let's see what happens. Okay, this point right here is going to be reflected over here, and this point way over here, and it's going to be curved. Okay, and this yellow region is going to be reflected on the other side onto the blue region, and what you're going to have is our disk orientated in a horizontal fashion. So if we drew, let's say, let me draw the cross section right here. Yeah, here's one disk right there. There's a disk. There's a cross section right there. The question is, how do you set this one up? Okay, so let's talk about that. Well, the radius now is here. This distance is the radius. And this radius is now not a function of x, it's actually a function of y. Because this distance is now, if you come down here to the x-axis, let's say this is the x-axis right here, it's, some length x. But what is x equal to? Well, you're going to have to solve your function in terms of y. You're going to have to solve for x in terms of y. So we say it's f of y now. It's a function of y. Up here, the radius right here was equal to some y value right here. And so the radius is equal to y, okay, and that's equal to some function of x, and that's why I had to write the radius in terms of x right here. But now our radius is in terms of y if it's horizontal or perpendicular to the y-axis. In this case, your volume is going to be found by taking the integral from c to d, because the disks start at c and go all the way up to d. That's how they're built. So we're going to integrate from c to d, pi times radius squared, but this time the radius is a function of y, so I'm going to write down r of y, quantity squared, dy. So again, we're going to have to solve for the radius in terms of y. Solve for we'll solve for x in terms of y. Let's just say that way. Solve for x in terms of y. That's what you're going to have to do in this case. And I'm going to go through an example here so you can see it in action. But that's basically what you're going to have to do. Now it's a little bit vague and a little bit abstract, so let's get right into an example and let's show you how it's done. Okay, so we're going to take a look at two situations here. One, we're going to revolve around the x-axis right here. That's what it says we want to do about the x-axis. And the second example, we're going to revolve around the y-axis. The very first thing you're going to have to do is you're going to have to graph the bounded region. So first, graph bounded region. You're going to have to do this on your own. In our example here, I'm illustrating the idea, so I came up with these computer drawings. But what you're going to have to do is interpret this. Okay, find the volume of the solid form by revolving the region, this right here, this region, about the plane given this condition. Okay, in the first part right here, 0 is greater than or equal to y. Now, if 0 is less than or equal to y. If that's the case, y is greater than or equal to 0, and that means that you're above the x-axis. That's what that means. Above the x-axis. And you'll notice that our bounded region is above the x-axis here. The second portion, y less than or equal to root x, that means you're below the function. So you're below the function here. So what you do is you graph root x. You graph y equals root x. You can use a table of values. When x is 0, root x is 0. And so you plot the 0, 0 there. This is from 0 to 4, it says, right? So this is 0, this is 4. And then you let x equal 1. Root 1 is 1, so you plot 1 comma 1, be right about here. Because if this is 2, this is 1, so, no, 1, 1 here. There's 1, 1. If you substitute 4 and you get 2, so 4 comma, right here, 2. So this is 4 comma 2. Okay, sorry about that. Let's get back into it here. So what you're going to do is you're going to take this bounded region here that's given by your conditions here in the problem. We're between 0 and 4. We're below the function here. We're above the x-axis. And what you want to do is revolve it around the x-axis. So we're going to revolve it this way. We're talking about the x-axis. So this bounded region that I illustrated here can be seen in the three-dimensional graph. It's the same thing right here. And what we want to do, if you're going to do this on your own without my help here, is you're going to have to reflect it over here below the axis. This point, it's 2 units above, so it goes 2 units below. I would highly suggest you do this every time you work on these, just so you can see it. Draw a typical cross section here to see the disc. And this is, of course, the disc right here. And then, of course, draw it in 3 dimensions here. What does it look like? Okay, a disc looks like that. So I just drew a couple, so you can see it. The question is, what is the radius? What is R right here? What is that radius? R. That's the very first thing you got to figure out. The thickness right here, the thickness of the disc is, since it's vertical here, is the difference in x's. So we call that dx here for the thickness. So we want to write our integral in terms of x. So we got to write our radius in terms of x. Well, what is x equal to right here? Well, it's equal to some y value, first of all. And that y value is given by your function. It's given by root x. Okay, so you can see right here in our first example that r is not a fixed value. It's not a real number like 4 or 10 or 15. It's a function of x. It depends on where you are in the cross section. So if you drew it here, obviously r is shorter. All right, it's given by the function root x. So you have to write it as a function of x. The disk volume, call it dV for short, is found by taking pi times radius squared, all right, times how thick it is, which is your dx in the integral. Okay, so what you want to do is substitute in your radius, okay, because it's always pi times radius squared. Well, you want to simplify that a little bit. So when you square root x, you just get x, and so you get pi times x dx. That's called your disk volume. Well, you want to find the total volume. That's our end goal. And our bounded region is from 0 to 4. So A is 0 and B is 4 in this example. So our volume now is from 0 to 4 of pi x and dx. Let me rewrite that a little bit better here. Pi x dx. You want to integrate that from 0 to 4. So if you want, you can pull out the pi. So it's going to be pi times the integral of x. And what's that? Well, it's x squared divided by 2, evaluated from 0 to, not 2, but 4. Okay? So it's going to be pi halves times, whatever 4 squared is. So 4 squared, 16, minus 0 squared, 0. So you get 8 pi in this case, cubic units here, because that's volume. So believe it or not, it's actually pretty straightforward and pretty simple, as long as you know how to find the radius. You just take pi times radius squared, multiply it by dx for your thickness to get the volume of one disk, and then the integral sums them up all for you from 0 to 4 in this case. All right, now that's an example dealing with disks that are vertical, which are perpendicular to the x-axis or revolving around the x-axis here. What happens if you revolve around the y-axis? Well, let's take a look at that. We have a function, or first of all, we want to find the volume, all right, of the solid form by revolving this region here that's given to us here about the y-axis. So what I would do, if you're going to do this by hand here, is I'd develop some table values in here. I'd substitute 0 in there. And, nice perfect squares, because you're going to have to square root them. Like, 1 would be good, 4 would be good. Okay, and so you can figure out what's going on. So if you substitute 0 in, you get 2 times root 0, which would be 0. 2 times root 1 would be 2. 4 times root 2, or excuse me, 2 times root 4 is 4, and so on. You graph the function. Y equals 2 is a horizontal line there. Y equals 2. X equals 0 is this line here. X equals 0. It's the y-axis, of course, and your bounded, and your function here, 2 root x, is this curve. Here's your curve right here. And this is y equals 2 root x. And so what you do is you bound this region. That's the very first thing you do, is you graph your bounded region and then determine how to revolve it. And in this case, we want to revolve around the y-axis. So this way. So this region here that I just illustrated here is seen in the three-dimensional graph. It's right here. It's the same thing. Okay. The question is, how do you form the radii, or how do you form the disk? Okay. Well, first of all, if you're doing this by hand, you might want to revolve or reflect this across the y-axis here, so you can see the other half in blue here. And that's this portion over here on the left side. And then draw a cross section here. Your disks are going to go this way. They're going to be horizontal or perpendicular to the y-axis. Okay. And then if you want to see some disks, you just have to draw them. You can see one here. Okay. So then, oops, you got to figure out the radius. And now the radius is, it's equal to some x value, not y value. This is equal to x on the x-axis here. What is that radius? R. I'm talking about right here. What is R? Well, we got to figure that out, like I said. Well, it's equal to some x value, and that x value is given by this function right here. So what we need to do is solve for x. So what you do is you take your function over here, and it's y equals 2 root x, and you got to solve for x, just using some basic simple algebra. So let's start dividing by 2, and you get y divided by 2 equals root x here. And you got to square both sides, and so you get y squared divided by 4 equals x. So if the radius is equal to some x value there, which is given by the function, then x must be y squared divided by 4. So y squared divided by 4, that's your radius. After this, you can find your disk volume, dV. So the disk volume in this case would be pi times radius squared, or y squared divided by 4 squared times your thickness. But your thickness this time, well, it's a difference of y values now, so we're going to call that dy. And that's your thickness, dy. Okay, so times dy here. When you have horizontal disks, the thickness is dy, and you're going to have to write the integral in respect to y to find your total volume. Now, the limits of integration are not found left to right or horizontally. They're found by building your disk from low to high. And we're going from 0 to 2 in this case. So a equals 0 is our lower bound. We're up at height 2 here. So when you substitute 1 in, you get 2 back. So from a equals 1, or a equals 0 to b equals 2. All right. So we're going to integrate now from 0 to 2. Pi times whatever this is squared. And I would suggest you simplify this. When you square the fraction, you get y to the fourth divided by 16. So y to the fourth now divided by 16 dy. Let's simplify that a little bit. Let's take the constant out, the pi 16ths. Okay, integrate from 0 to 2 of y to the fourth dy, which is much clearer and easier to see. And so what do we get? We get pi 16ths times y to the fifth divided by 5, evaluated from 0 to 2. So what do we get there? We get pi 16ths times 2 to the fifth divided by 5 minus 0. Well, that's 32 divided by 2, which is, well, I didn't write this correctly, divided by 5. 5 here. Okay, there we go. That's 32 divided by 5. So what do we have? You have pi 16ths times 32 fifths. As you guys know, this is 2, and so what we get is 2 pi fifths. 2 pi fifths cubic units. And that is the exact volume, believe it or not. Okay, 2 pi fifths cubic units. That's the volume of the solid revolution if you revolve it around the y-axis there. So keep in mind when you're doing your homework, if your disks are horizontal, it's going to be a dy integral. Integral involving y and dy. And if your disks are vertical, the thickness is dx, you're going to have to write your integral in respect to x and have a dx integral. You only have those two cases. Later on, when we revolve around lines other than the x and y axis, we're going to have holes in the disk, and we're going to call them washers. We'll see that in the next lesson. Right now, what I want you guys to try to do in this homework are the first 3 problems. Okay? This is lesson 16. This is the disk method. Okay, disk method. So give that a shot. Check the solutions online. All right, check online for my step-by-step results. The answers are here, obviously. Okay, so those are your goals. But step-by-step is online. Okay, good luck. Try the first 3, and we'll handle the rest later. See you tomorrow.